right, lesson 1.2 is rates of change. So in lesson 1.1, we learned that the slope of a line can be interpreted as its rate of change. If the graph of a function is not a straight line, we use the terminology of an average rate of change between any 2 points on its graph. So what it is the average rate of change is really just a slope between 2 points on a non-linear line. So for example, if I have this quadratic function and I want to know the average rate of change between this point and this point, I'm looking for the slope of the line that connects those 2 points, okay? Which is called a secant. All right, so the average rate of change between two input values is the total change of the function's values, the output, divided by the change of the input values. Given the value of a function at different points, we have x1, y1, and x2, y2. Your average rate of change on the function f on the interval from x1 to x2, where f of x1 is equal to y1 and f of x2 equals y2. Remember, we know also that f of x is equal to y. So if I say f of x1, that's going to be equal to my y1, okay? Same thing if I put x2, then it would equal y2. All right, and then your average rate of change, I told you it's just your slope. So it's going to be the change in the y's over the change in the x, or y2 minus y1 over x2 minus x1. All right, so let's look at example 1. It says the table below gives output values of the function f of x for selected input values of x. Find the average rate of change from x is 0 to x is 3. So we're looking from where x is 0. Oops, I didn't turn my pen on. I'm really bad about that. I apologize. X is 0 to where x is 3. So this is my x1, y1. This is my x2, y2. All right, and so I know that my average rate of change is equal to my y2. Well, actually what I'm going to do first here is I'm going to set up a skeleton. And a skeleton has a fraction line and it has the minus signs. Because sometimes if our x1 or our y1 is a negative number, we forget the minus and the negative. We just put it once. So I'm going to set up a skeleton and then I'm going to plug it in. y2, y1, x2, x1. And we'll work this out when we get 9 over 3, which is 3. All right, so some essential knowledge here. A positive rate of change indicates that as one quantity increases or decreases, the other quantity does the same. So if x increases, the y increases. As x decreases, the y decreases. If the rate of change of f is positive, then the graph of f is increasing. A negative rate of change indicates that as one quantity increases, the other decreases. So if one is positive, the other one would be negative. All right, if the rate of change of f is negative, then the graph of f is decreasing. The rate of change at a point, called the instantaneous rate of change, can be approximated by the average rates of change over small intervals containing that point. So you'll see that at times we'll kind of squeeze in and that towards a point, and that's where we're trying to find that instantaneous rate of change. It's going to be the slope between 2 points that are super close to the point we're looking for. So if I'm looking for at 1, it's not going to be just 0 and 2. It's going to be like 0.99 and 1.001. Okay, it's going to be squeezed in on it. All right, look at example 2. It said find the average rate of change of f of x equals negative x cubed minus 2x over the interval from negative 1 to 3. All right, so that interval is my x1 and my x2. So I'm going to go ahead and set up two ordered pairs here. My first one, I know my x1 is 1, and I don't know my y1 yet. And then my second one, I know my x2 is 3, but I don't know my y2 yet. So x1, y1, x2, y2. Now, in order to find my y1, remember we said above, that's the same as f of x1. And so this would be the same as f of negative 1, which means I'm going to plug negative 1 into my equation. So I'm going to do my skeleton. So it's negative x cubed minus 2x. Remember, a skeleton is like the bones of the problem, okay? So it's not going to include any variables. And where you had a variable, you're just going to leave a space for it to plug something in. Typically, I will use parentheses. All right, and what are we plugging in? Plugging in that our x here is negative 1. All right, so I'm going to work that out. And let's see, I get, let me write it underneath it actually, save a little room there. So we have a negative 1 cubed is negative 1, and then plus 2. So negative, that's 1 plus 2, which is 3. So I know my y1 is 3. Then I'm going to do the same thing to find my y2. Remember, that's just f of x2, which my x2 is a 3. So I'm going to do my skeleton. And then I'm going to plug in the 3, and I'm going to work it out. So that's what negative 3 cubed is 27. Minus 6, that's what, negative 33. And now that I have that, I can go in and I can find my average rate of change. So my average rate of change is going to be y2. Well, let me do my skeleton. Sorry, y2, y1, x2, x1. And so I get negative 36 over 4. Well, for some reason my pen's not writing here. There we go. Which is negative 9. All right, in example 3, says the table shown above is data from the University of Michigan Center for Sustainable Systems. It shows the U.S. Annual Municipal Solid Waste, or MSW, generation. MSW is commonly called trash or garbage, which generally refers to common household, office, and retail waste, but excludes industrial, hazardous, and construction waste. A says find the average rate of change in trash between 1985 and 1990. Okay, so we can see in 1985 and 1990. So there's the numbers we're using. So our average rate of change, I'll do my skeleton. So it's I'm going to let this be x1, y1. This will be my x2, y2. So it's going to be the 208.3, 166.3, 1990, and 1985. All right, so I'll work that out, plug it in my handy dandy calculator, whichever, and we end up with 8.4. Now, because it is a word problem, we need to go ahead and label it. So 8.4 what? Well, what is my Y's? My Y's are the millions tons, right? Million tons. And what are my X's? Well, they didn't label it here, but we can see it's the years. So this is going to be million tons per year. All right, and then B says describe the average rate of change found in part A in context. Well, because we labeled it, it makes that pretty easy. So the rate is it increasing or decreasing? Well, since our average rate of change is positive, that means it's increasing. By 8.4 million tons per year. But now you've got to be a little specific. The slope is only between 1985 and 1990. So the rate is increasing by 8.4 million tons per year from 1985 to 1990. Or you could have used the wording they did and said between 1985 and 1990. Either way. All right, moving on. So then it says, how can you find the instantaneous rate of change? The concept of instantaneous rate of change, or IROC, is formally developed in calculus, but we will approximate the rate of change at a point by calculating the average rate of change over very small intervals. All right, so look at example 4. It says, suppose an object is launched upward from a height of 120 feet with an initial velocity of 48 feet per second. The height of the object t seconds after its launch is given by h of t equals negative 16t squared plus 48t plus 120. Find the average rate of change in the height of the object over the given intervals. Include units of measure. All right, so they're telling us on A, when x is 1 to when x is 1.1. So I know it's going to be 1 comma something and then 1.1 comma something. So we need to go through and find this. We could work it out, but with the numbers being, if you look at D, this would be on a calculator section. So let's go ahead and let's put our equation into y equals. And if you don't know how to make your calculator look at all different values, I'm about to walk you through it. So I'm going to go to y equals, put in my negative 16x squared plus 48x plus 120. Now if I go to my table, I can find 1, but it also has 2, 3, 4, 5. It doesn't have 1.1. So what you can do is if you'll go to second window, and you see where it says independent, INDPNT, and it says auto, change that to ask. So it's going to ask you what X values do you want me to look at. All right, so change it to ask and then go to your table. Now, unless you didn't clear your calculator, your table's probably blank. So now I can go in and I can type in 1. Under the X, I'll put 1, hit enter, and it tells me 152. Then on the next line, I'm going to put 1.1. It tells me 153.44. Now, I'm going to go over on that actually and make sure it is 153.44 exact, because in AP Pre-Cal, we round to 3 decimal places in our final answer, which means if I am having to round in the middle of the problem, I need to go more than 3. I need to probably go at least 5. Okay, 2 extra, so that way when I round at the end, it's still going to round correctly. All right, so if I arrow down to the, if I arrow over to where it says 153.44 and look at the bottom of my screen, it tells me at the bottom it's exactly 153.44. So I know I'm using the exact value there. All right, then we can go find that average rate of change. So we know it's going to be, let me do my skeleton. Sorry, there's my divide, my minuses. It's the 153.44 minus the 152 over 1.1 minus 1. And it's going to tell me that it is 14.4, and it says include the labels. So let's see. My height is on top. That's in feet. And on the bottom is my X's, which is my time, T, and it says that it's labeled in seconds. I can tell right here, this helped me out. It gave me a little clue right there what my label would be. Okay. All right, let's do the same thing for B. So we know that 1 has a Y value of 152, and we got to go find for 1.01. Well, go back to your table. It's still in the ask mode, and type in 1.01 and hit enter, and it tells you 152.16. Now I'm going to arrow over on that, and I can see that it's actually 152.1584. So I'm going to use that value because I don't want my rounded value at the end to be off. Then when I go find my average rate of change, Y1, forgot my bottom minus sign, didn't forget it, it just didn't show up, 152.1584, my Y2, my X1, my X2, I may be saying it wrong, Y2 minus Y1 over X2 minus X1. I'm going to type that in. And again, my units are feet per second. All right, C, we're going to do the same thing. So I already know the ordered pair for 1. But for the 1.001, I'm going to go back to my table. I'm going to type it in. I see it says 152.02, but I'm going to scroll over on it, and I see it's actually 152.0159. I need at least one more. It's only got an extra one, so I'm just going to use the whole thing there. All right, so my average rate of change is my Y2. And if you don't want to keep writing, like you don't want to write that number out, so you don't have to write it, you could use symbols. So let me show you. Now, we're not going to just put Y2, okay? You got to be a little fancy here. So you could do, it's the F of, what was its X value? The 1.001 minus the f of what was the 152, what was its x value? 1 over, and then you could type in your 1, or write down your 1.001 minus 1, like that. It's another way you could do it, so you don't have to write out that whole number, but you do have to type it in. All right, so we go through, we type it all in, 152.015984 minus 152 over 1.001 minus 1, enter, and it tells me 15.984, and it's feet per second. Like I said, we're going to round to 3 decimal places, and honestly, you can either round this last number or you can truncate it, which means cut off everything after it. So either one is accepted on the NAP pre-cal. All right, and then D. On D, notice now they took the 1 out, so now we're going to have to do both of them. So I've got 0.999, comma, I got to go find its Y value. And I can see it's 151 point. I'm going to arrow over so I can see all the digits. So 983984. Sorry, it's a little spread out there. And then 1.001, we know it, we just did it. That's our 152.015984. All right, so now when I go to write this, I'm not really excited about writing both of those really long numbers, so I'm going to use that function notation like I did in the other. So it's going to be my y2, which is what I got when I plugged in the 1.001, minus my y1, which is what I got when I plugged in the 0.999, over my x2 minus my x1. Okay, so I'm going to type in all those numbers, and I end up with exactly 16 feet per second. All right, well, notice on that one, what number is really close in between, let me change colors here, really close in between these two numbers. They're squeezing up on 1, right? Which means by using that 0.999 and the 1.001, we are finding that instantaneous rate of change at the number that's right in between them, which is 1. All right, so E says, using your rates above, what is your estimate for the instantaneous rate of change in height of the object at time t equals 1 second? And so at t equals 1, at t equals 1 second, the instantaneous, I'm going to do no, we need to write it out because it's a word problem. Instantaneous, I'm going to run out of room. Sorry. Instantaneous rate of change is that 16 feet per second. All right, example 5 says describe the graph and the rate of change for each of the following graphs shown below. All right, so look at A, the graph of H. It says the graph of H is, all right, so we can see that it's going down, so we know it is decreasing. Also notice where it's at. It's above the x-axis, which means all of the y values are positive. So the graph of H is decreasing and positive. Now I'm going to jump over to B real quick here because let's look at that graph of K. Notice it's increasing, it's going up, but all of them are below the x-axis, so all your y values are negative. So it's increasing and negative. Now, when we do the next part, we're talking about the rate of change. We're talking about the slope. So, all right, so if I look at the graph of H, I'll notice it's concave up because it looks like the side of a cup, all right? So remember, with concave up, our slope is increasing, okay? The rate of change will be increasing because as I am more negative there than I'm negative here, okay? Then I'm negative here. So my rate of change is increasing. I'm getting closer to the positives, but just a part of the graph we can see we never actually hit a positive. So our rate of change is still negative. So the rate of change is increasing and negative. Now when we go over the graph of K, notice it looks like a frown. So this is concave down. So when I'm looking at this average rate of change, the slope of those little lines I just drew in are positive. So we know the average rate of change is positive, but each one of them is less and less steep. They're not as positive as the previous one, which means if it's not as positive, it's getting smaller, so it's decreasing. So this one is positive and decreasing. All right, in example 6, it says use a function g of x equals negative x squared plus 2x plus 1 to complete the following questions. A says what is the average rate of change on the interval from negative 1 to 2? All right, so I know x1 is negative 1 and x2 is 2. I got to go find their y values. All right, so I could use my calculator again, or I could work it out. Either way, these numbers aren't too bad. But when I go and I plug in negative 1, it's going to tell me that it's at negative 2. And when I plug in 2, its y value is positive 1. So when I go to find that average rate of change, I know it's going to be my y2 minus my y1 over my x2 minus my x1. All right, use the average rate of change to predict the value of g of 1. All right, well, we know that this 1 is in between these two. All right, so we're going to use the line that connects those two to help us predict the value. So we know 2 points and we know the slope. So I'm going to pick one of those points. And I know that my slope was the 1. And this one right there is that one, okay? So going back to algebra 2, we know if we have a point and a slope, we can use the point slope form, which is y minus y1 equals m times x minus x1. And remember in this one, we plug in our x1, our y1, and our m. This is going to give us the line, equation for that secant line. Remember I mentioned the word earlier. The secant line is the line that connects those 2 points on a nonlinear graph. All right, so let's see. We got y. I'm going to build my skeleton. I'm going to plug it in. So let's see, my x1 is negative 1, my x2 is my y1 is negative 2, and my slope was 1. So when I start working this out, I get y plus 2 equals 1 times x plus 1. So y plus 2 equals x plus 1. Subtract the 2, so y equals x minus 1. All right, so that's what I got for my secant line. Now, if I'm looking for a g of 1, I'm just going to plug that in to that equation. So I know that, well, let me write this. So I know that g of x then will be x minus 1. And so g of 1 is 1 minus 1, which is 0. So predicting the value of g of 1, we believe it's going to be 0. All right, without finding g of 1, would your estimate from part B be above or below the value of g of 1, and how do you know? All right, well, let's think about this. So if we look at our equation, it's quadratic and it's negative, so we know it's going to open down. All right, so, and if I pick 2 points on here, and it really doesn't matter which 2 points. I mean, I'm going to, not knowing exactly where the negative 1, negative 2 is, and the 2, 1, the points are, it wouldn't matter where I put them on here. So let's just say it's here and here. We're going to get the same thing. And so when I draw in that secant line, or the line that connects them, it's going to be below it. It would be the same thing if one of my points was here. Instead, it would still be below it. Or if I was connecting these two, it's still below my curve, okay? Let me back up here then. Okay, so either place we place our points, it's going to be, when we draw our secant line, it's going to be below the actual curve. All right, so because the secant line lies below the curve, whoops. All right, so since the secant line lies below the curve of g of x, and the graph of g is concave down. I'm just going to do and g of x is concave down. That's how we know it's below it. The estimated value, because our estimated value is going to be the one that's on that secant line. Remember, we found the equation of the secant in B, and we used it to find the thing. Well, it's going to be like right here. So it's actually below. So it's going to lie below the value of g of 1. All right. Since the secant line lies below the curve of g of x, and g of x is concave down, the estimated value and I'm so sorry, I'm going to have to come up here to finish my sentence. Okay, so the estimated value lies below the actual value for g of 1. All right, so notes about the big ideas. So in AP Pre-Calc course, we cannot find the exact rate of change of a function at a single point. Our techniques will be able to recognize that the instantaneous rate of change is the slope of the graph at a single point. Therefore, we do one of the following. So we're going to estimate the rate of change at a point using the average rate of change over a very small interval, or we can estimate the rate of change at two different points using concepts of a tangent line. All right, so a tangent line is different than a secant. So we had said, real quick, let me explain the difference. So if I have some graph here, the secant line is going to be the line that connects those 2 points. It's a line that goes through, if you remember from geometry, it's a line that goes through, but it's not the center of the circle. Through the center of the circle, same thing here, okay? It's a line that connects 2 points on the graph. Now, a tangent line is going to be a line that touches the graph in 1 point and then moves on. So if I'm looking for the instantaneous rate of change on that, the tangent line is going to come up, it's going to touch at that 1 point, and then it will continue. So we could use the tangent line if we knew it, because it'll have 2 points on it as well, and its slope is going to be the same slope that's at that point. So we could use that. So you could use either one is what it's telling you. All right, so continuing on then. A summary of the graph behavior and the rates of change. So the rate of change of f is positive, then we know that our graph is, if it's positive, it's increasing. And so if it's negative, it's decreasing. Now, if the rate of change is increasing, that means our graph is concave up. And if it's decreasing, our graph is concave down. All right, word of caution. When answering questions about graphical behavior, watch the language of each statement. Is the prompt referring to the graph of f or the rate of change of the function of f? You have to be very careful. I see that getting mixed up a lot, so watch out when they're asking you those. All right, in example 7, The one you've been waiting for, the last one in this lesson. It says the graph of G is shown at the right. Complete the statements below to describe the graph of G and the rate of change of G. All right, so the graph of G is, well, the graph itself is going up, so it's increasing. And it's concave. You can see it looks like a side of a cup, so it's concave up. Because the rate of change of G, now the rate of change, look at the slopes. What's happening here? If you don't have it memorized, what concave up does, you can see your slopes are getting more and more positive. So the graph is going to be, the rate of change of G is positive, and the rate of change of G is, and they're getting more and more positive, so they're increasing. All right, and that is lesson 1.2.